So welcome to the second part of the thermal chem unit. Today we will look at calorimetry. After having defined a few terms such as exothermic, endothermic reactions, thermal energy, heat, and of course enthalpy. So calorimetry is a way to experimentally calculate heat, in other words, the exchange or movement of thermal energy. So this can be done experimentally, which is what we'll look at today, and the next 3 or 4 days we'll look at other methods named here, so we'll get to that shortly. But first, let's review a bit. So looking at this energy time graph, we see that this can be either exothermic or endothermic. We'll look at our reactants and the amount of potential energy they have compared to our products. Reactants being methane and oxygen in a complete combustion producing CO2 and water. See that our reactants have a certain amount of thermal energy. Let's take out a highlighter or even a pen. So they have a certain amount of thermal energy, and the products have less thermal energy. So this difference in thermal energy, delta H, is lost. It had some arbitrary number, let's say 100, and now it has 10 joules. So this negative 90, in this case, not negative 90, it's 890 kilojoules, is lost from the system. So released out into the surroundings. That makes this reaction, give you a moment to decide whether it's going to be exo or endothermic. If you're thinking exothermic, you are correct. So that will make this reaction an exothermic reaction. So just to quickly review that again. Reactants begin at a higher potential energy with a certain amount of activation energy. In this case, it's probably going to be a spark, an ignition of some kind of flame, reach its activated complex really quickly, and doesn't exist for long at all, then quickly reacts and produces your products at a much lower potential energy. Releasing this from the system, losing energy, surroundings then gaining. And that leads us to calorimetry, an experimental method to determine in a closed system using a substance, usually water. In our high school experiments is what we're only going to use. So we are indirectly measuring through, well, perhaps directly measuring through heat. So through the transfer of thermal energy, we're measuring Q, heat, and that will allow us to determine how much energy the system has lost or gained. This can therefore be positive or negative depending on the reaction. So to review that in math terms with variables, we see that energy can be positive or negative. If a system is positive, so it's gained energy, it must have gained it from somewhere, so it must have gained it from its surroundings. That means the surroundings is lost. They have lost energy. So unlike the exothermic example, this is an example of an endothermic reaction. So imagine having an ice cube in your hand. You feel cold, and you feel cold because that ice cube is taking energy from your hand, its surroundings, and it's gaining that energy in its system. It's melting the ice cube into liquid water. So essentially you'll have opposite or opposing signs here, one positive and one negative. Now this can be directly related to the enthalpy of the reaction, or in the ice example, the enthalpy of the phase change from solid to liquid. In which case this little subscript here would change. It can right now be R, it can be VAP for vaporization, it can be melting from solid to liquid, but we'll get into that some more later. So we do this, we measure this using two types of apparatus. One is a coffee cup calorimeter and the second a bomb calorimeter. Before we get into that, I'm just going to briefly mention what we will talk about more next time is molar enthalpy. Another way of measuring heat transfer is through molar enthalpy. There's the mole again, so we will see that shortly, but for now we're going to look at two types of calorimeters, coffee cup and that is the actual name, and a bomb calorimeter. Here are pictures of both. Just make this a bit smaller there. Okay, a coffee cup calorimeter involves a double styrofoam cup and a cover, of course. We want to make sure that this heat that is lost or gained isn't lost to the environment, isn't lost to the or released from this apparatus or absorbed by the apparatus. And we'll talk about the assumptions that need to be made in just a moment, but this is what the picture looks like. This is what your coffee cup calorimeter looks like. It will involve often a stir, although I like to try to avoid any perforations in the apparatus. Here is your thermometer, which is measuring change in temperature, and we'll see how mathematically that can relate to Q, the heat, and then change in energy. A bomb calorimeter is similar, except we'll get into the math. Math is actually a bit simpler. It's an entirely calibrated system, usually involving a combustion reaction held within a vessel that is within the larger vessel. We'll get to the math behind that. It's simpler than this you might think by looking at this picture. So a coffee cup calorimeter is measuring heat that is generated or absorbed from a reaction, Q, in other words, and that can be positive or negative. That is equal to the mass of the substance inside the calorimeter. Now this liquid is usually going to be water, so we need to find out the mass of water inside. And C is a specific heat capacity of water, which has been a predetermined, experimentally verified value. We'll get into that in just a minute. Times delta T, so that's change in temperature. So that's final minus initial temperatures. So a bit more on specific heat capacity. So that C is the amount of energy absorbed in joules divided by, or the amount of energy absorbed in joules per gram of mass per degree Celsius. So for every gram of water, a certain amount of energy is absorbed per degree Celsius. And these values, again, I'll show you in a moment, have been experimentally calculated. Now there are a few assumptions that have to be made when using a calorimeter, a coffee cup calorimeter, or both a bomb calorimeter as well. So we have to assume that no heat is being lost to the cup or to the equipment. Being a great insulator, styrofoam is actually really good to use and does give us these coffee cup calorimeters do give us pretty good, precise results. Also, that no heat is lost to the surroundings, but that is always a source of errors. There can be heat loss to the surroundings if maybe there's a hole in the coffee cup calorimeter, or if perhaps you are stirring and making that perforation in the coffee cup lid a bit larger, so there can be some heat loss, but we have to make these observations or these assumptions so that we can perform calculations. Referring now to specific heat capacity. So liquid water has a specific heat capacity of 4.18. And what that means is you need 4.18 joules for every gram for every degree Celsius of water. Different substances have different heat capacities. Solid water, 2.03, carbon, iron, chromium, aluminum, and so on. These are values that will always be given to you on quizzes, tests, or exams. You won't need to memorize these. A bomb calorimeter looks very similar to a coffee cup calorimeter, except notice that it has no mass. And that is because the bomb calorimeter has been calibrated so that the heat capacity is specific to that bomb calorimeter. So C will be a certain value unique to that calorimeter. So the mass of whatever liquid is inside, perhaps water, is not relevant. So, first example, we're going to calculate the amount of heat required to warm 1.25 liters of water from 22 degrees Celsius to 98 degrees Celsius. So roughly room temperature to almost boiling in an electric kettle. So this is how we do this. Although it doesn't say coffee cup calorimeter, we do have values that suggest that we can use this formula. And I should say something about this. We have Q is equal to M, the mass of water, times the heat capacity of water times delta T. Notice there is no triangle. I can draw a triangle, but this isn't a touchscreen, so I can't physically draw it right now. So I'm going to leave this as T, but know that it should be delta T. And we'll start our calculation. So we know that Q, we're trying to figure out what Q is. We can figure out what the mass of water is. Knowing the density of water is for every 1 milliliter of water, we get 1 gram of water. If we have 1.25 liters, we have 1,250 milliliters of water, which will give us 1,250 grams of water times a specific heat capacity, which is 4.18 joules per gram per degree Celsius. There should be a degree sign there. There isn't, so just make note that there isn't, only because I'm typing this out, but you should have it when you write your answers. Times 98, also degree should be degree Celsius, minus 22 degrees Celsius. We'll do a little bit of elementary school math and simplify. .76 degrees Celsius. Now I'll pause here because I want to show you that units are important. So we have grams over grams, they cancel out. Celsius over Celsius, they cancel out. What we're left with are joules. Joules are what we need because we're trying to figure out how much heat is required. So far we're doing everything well. Notice the fact label method continues to help us even in grade 12. So what we're left with after some simple calculations in our calculators is that we have 397,100 joules, and if we round that to something or change the unit something a little more practical, we have 397.1 kilojoules. Okay, not necessarily sig figs, but we'll just leave it at that for now. The next example, it's a similar question. It doesn't ask us, it doesn't say anything about a coffee cup calorimeter, but it does imply that we can use the given formula. So Q is equal to MC, remember there should be delta T, except it's not asking us for heat. It's already given us heat. So the question is, what mass of aluminum in a car engine will absorb 1 megajoule of heat when the temperature rises from 22 degrees Celsius to 102 degrees Celsius after the car is started? So it's not asking us for temperature, it's already given it to us. In fact, it's asking us for mass. So a little bit of grade 8, grade 9 math here. With isolating for mass, we get mass is equal to Q divided by heat capacity times delta T, which now I'll just write as that. So mass is equal to Q. Now Q, I put this chart here just so you can refer to, 1 megajoule of heat is 1 times 10 to the 6. So 1 times 10 to the 6 is 1 followed by 6 zeros. Joules. That's all divided by delta C. Now in this case we're looking at aluminum. Aluminum is not 4.18, that's water. Go back to our chart and we see it's 0.89. Again, these are values you will not need to memorize, it will be given to you on a quiz, test, or exam. So aluminum is 0.89 joules per gram per degree Celsius. Let's write C times change in temperature. So it's 102 degrees Celsius minus 22 degrees Celsius. So we can get straight to the point. I don't see that you can do simple arithmetic. So it's 80 degrees Celsius, and we can start to solve. Now again, here we can see that degree Celsius will cancel out, joules will cancel out, and we'll be left with grams. We'll be left with a mass of 14,044.9 grams, which is about 14 grams. Right, so that's it for calorimetry. Now briefly just lead us into what will be coming up, molar enthalpy. Delta H can have a different subscript. It can be delta H of, let's see if I can write this quickly, it can be delta H of vaporization. You saw delta H of reaction, it can be delta H of combustion. So delta H is essentially right now just change in potential energy, change in thermal energy of a different situation. It can be vaporization, it can be neutralization, combustion, it can be the formation of certain products. That will lead us to enthalpy and molar enthalpy that will be coming up next. To end off, you have a bit of home fun.